everyone, welcome back to yet another Euphoria Academia YouTube video. Today we're going to be doing the Physical Sciences Physics Paper 1 May-June 2022 paper that was done by the Matrix. My name is Ole and I'll be taking you through it. So today we're going to be doing electric circuits. We're going to be looking at the one question that appears in the multiple choice, as well as the meat, the substance of this question paper when it came to electric circuits, and that's question 8. And then we're going to do a bit of question 9 because that also needs an understanding of how circuits work. So without further ado, let us get into it. Right, so with the first one, we have a multiple choice question where essentially is asking us for the definition of the EMF, which is a popular term, or I wouldn't say popular, but it's something that you need to know when it comes to electric circuits, what the EMF of the battery is, and the definition that, or the statement that comes close to the definition is number D, and just like that, we have our 2 marks. Alright guys, so now we just got to question 8, which is the main part of electric circuits when it comes to this question paper. It starts from question 8.1 and ends at question 8.3.2. So let's not waste any time, let's get into it. Alright, first and foremost, I like to start by just analyzing what this circuit is. So that means explaining exactly what is going on, because that is going to help us going forward. So we're given a battery where we don't know the EMF, and the current will flow from the positive terminal all the way through this branch. And if switch S is closed, then we're going to have a parallel circuit, of course, right? But if it remains open, then we're going to have a situation where the current, there's not going to be current flow across the switch. So the current is just going to go through this 4 ohm resistor, and then through the 8 ohm resistor, and then back to the negative terminal of the battery. So if S is open, then our I is just constant. It'll stay the same. All right. However, we have a voltage divider circuit. This means that when current flows from the positive terminal and through this branch, when it gets to this resistor, we're going to have a voltage drop, and then here we're going to have a voltage drop, and then when it gets to the negative terminal of the battery, that'll be the circuit. Now V2 is actually measuring the external voltage, which will be the voltage drops of those 2 resistors. V1 is just measuring the voltage across this 4 ohm resistor, and then we have an internal resistance, of course, and the internal voltage in the battery will just be the current multiplied by the internal resistance, right? So there we have it. I think we can start with the question, and the first question is just asking us what well, it says that the 3 external resistors are ohmic conductors, and we just need to explain what an ohmic conductor is. And an ohmic conductor is essentially a conductor that obeys, oh, that's not how you spell conductor, a conductor that obeys Ohm's law. That's all. Is, yeah, Ohm's law. That is what a conductor is. And yeah, let's get into the questions that actually ask us for calculations. All right, so for question 8.2.1, we are asked to find the current through the battery. Now, as we established before, in this case, from question 8.2, the inception of question 8.2, we are told that the switch is open, right? And what that means is that we have a voltage divider circuit where the voltage is the one that keeps on changing through every resistor while the current is constant. So the current flowing through this is constant. So that means if we know the voltage and the resistance at one point, then we actually know what the current will be, right? And we're told that V1 reads a value of 3.2 volts, right? So that's the voltmeter across the 4 ohm resistor, right? So the current is equal to our voltage divided by our resistance, and our voltage in this case is 3.2 volts, and that is divided by a resistance of 4 ohms, and we're going to see that the current that we do get is equal to 0.8 amps. Right, still switch S is open and V1 is still giving us that reading of 3.2 volts, right? And we're asked in question 8.2.2 to find the EMF of the battery. Now, we know what the current is, and we can now get the resistance. We know the internal resistance. So essentially, we just need to find big R, which is the external resistance. And in this case, what we're going to see is that our R is equal to our 4 ohms plus our 8 ohms, because these resistors are in series, and that is going to give us an answer of 12 ohms. So we can finally substitute it into the formula of EMF, which is epsilon is equal to our total current multiplied to to the sum of our resistance. Right, so that's going to equal 0.8 multiplied to 12 plus, we were told that is 0.5, and that is going to give us an EMF of 10 volts. Now when we get to 8.3, we're told that switch S is closed, and when switch S is closed, we know that our V2 is going to be 8.8 volts. Now, you should know, or as stated in the analysis of the circuit, our V2 is actually our external voltage. All right, now question 8.3.1, right, is asking us to calculate the resistance of R. So now we have a full parallel circuit, right? So that means there's just a couple of things that we need to get before we can get to the resistance of R. We need to know the potential difference across the parallel circuit. We also need to know the current that will flow through the branches of the circuit. So our I1 and our I2 essentially. All right, so let us begin the question. So as stated before, our V external is going to equal to our 8.8 volts, and we know that our EMF is actually equal to our V external plus our internal voltage. All right, so how we get to know our V internal, because remember in the earlier analysis we established that our V internal is equal to our current multiplied to our internal resistance. Now our current has changed as well, because now we have a parallel circuit, so things have changed. All right, so let us find our V internal. So we know our EMF is 10 volts. That didn't change. We didn't change the battery. Our V external is 8.8. We were told that, and we just need to find our V internal, and that is going to give us an answer of 1.2 volts. Now from there, we know our V internal, so we can get the current across the whole circuit. All right, so let me just write it here to keep things clear for everyone. So current through whole circuit. I just should have said the total current, because this is a whole lot of words, doing a lot of yapping today. All right, cool. So as stated earlier, our Vn is our current, total current multiplied to our internal voltage. We know that our Vn is 1.2 volts, which will be equal to a current, and that will be multiplied to 0.5 ohms. Our internal resistance also did not change because we didn't change our battery, and we will find that our I is actually equal to 2.4 amps. All right, so now we need to figure out how much current is flowing through our R. All right, so by doing that, we're actually going to do it sort of like in a reverse way by determining how much current is flowing through this branch, so the branch of the series resistors. Because if you get that, if you get I1, then you can just say I2 is equal to the total current minus I1. That's the situation that we're trying to get to right now. All right, now what is the current flowing through that? So we know our resistance, right? And we know that current will remain constant across resistors in series. So let us formulate that. So our I, or our I1, let's call it I1, is going to be equal to our voltage, our voltage divided by our resistance, right? Now to note, this voltage is actually 8.8 volts, our V external, because in a parallel circuit, the voltage is the same across each branch, right? So that's going to be 8.8, and that resistance, we need to add our resistors, and that's going to give us, because even this 8.8 is across both of them in that branch, right? So that is going to be 4 plus 8, which is going to give us 12, and our I1 is actually going to be a value of 0.73 amps, and like we said before, our I2 will be equal to our I total minus this I1 value that we have. And where did we write our, there we go. That's going to be our 2.4 minus our 0.73. And that is going to give us a value of 1.76. I'm rounding off, by the way. And that would mean that the resistance finally is equal to the voltage divided by the current, which is our 8.8. I'm sorry for just squeezing everything in. I just want to write everything on one page. 8.8 divided by 1.67, and we will find that our resistance is 5.27 ohms. So that is our answer. And yeah, this was a bit long-winded, but hope you guys got it. All right, so the last question of question 8 is question 8.3.2, and we are told that the battery becomes heated when voltmeter V2 is replaced by a connecting wire. Why does the battery become heated? Well, if you remove this voltmeter, right, let's just say we don't have a voltmeter. Let me draw the battery here. Let's just say that's our battery, right? And we have a situation where it's like this. So essentially, the positive terminal of the battery is connected to the negative terminal of the battery, and current will now flow in this direction. All right. So when we have a situation like that, we've just created a short circuit, right? And this path that we just created actually has little to no resistance, right? So little to no resistance, right? So one can say after removing that voltmeter V2 that the resistance has decreased, right? And when the resistance decreases, the current through that path will also increase, not decrease. It will increase sharply. All right. And when it increases, this current is the one that actually makes the heat, right? So current is the one that produces the heat. And we can see that produces heat. And we can see that in the following equation where we use the power equation. So power is equal to I squared multiplied to R, right? So we know that our R decreased, but our current increased, right? Now, if it even increases slightly, it's even increased by the square of that amount, right? That would mean that the power dissipated, which also can be thought of a measurement of the energy. So the energy produced, the energy produced will be more, and this energy is in the form of heat. So that's how you can explain what is happening here. All right, as promised, we're going to do the circuit in question 9, and essentially both of these questions are worth 9 marks when you do the circuit, that is. They're worth 9 marks, but this section on AC was worth 12 marks, so 9 just calculations. All right, and we are told that a resistor Y is rated at 220 volts. You know what? I think let me do it in the next one where we can focus on question 9.2.1. Question 9.2.1 asks us to calculate the resistance of resistor Y. Now, resistor Y is rated, and now I'm going to write all of this in red because it's very important. It's rated for 220 volts at 100 watts. All right, and it is connected to a 220 volt AC source as shown in the figure. So this is a very simple circuit. No other things are happening here. Power or the current moves from here through here and then back again there. But because it's AC, it does it both ways. All right. But I wanted to focus more on what this rated means. This rated means it operates in these parameters. So it can't go above, I'm just going to do an X here, can't go above or below that rating. Another X here, or a star, right? Let me just say can't. It can't go above or below that voltage rating or that power rating. Otherwise the resistor will not work. Sometimes that might be a light bulb or anything of that nature, but it will not work outside of these parameters. So that's very important to note. All right. So enough yapping. Let us get into question 9.2.1. Question 9.2.1 is asking us to calculate the resistance of resistor Y. Right? So that's pretty simple. Right? So we know that we're given a wattage rating, so we can just use the power equation. Power is equal to, and we're trying to find the resistance, and we know the voltage, V squared over R. In this case, this V will be our V RMS, and we know what our power is, and that is 100 watts. That will be equal to our 220 squared over R, and our resistance will give us a resistance of 484 ohms. All right, for question 9.2.2, we have things that have changed, right? So another resistor Z with the rating, I think let me just write it here. So the rating of Z is 220 volts. We don't know the wattage, so the power, we don't know the power. And it is connected in series to resistor Y and to the same AC source. Right, the power dissipated by resistor Y changes to 80 watts. Right, so that means the power that is dissipated there is going to give us 80 watts now, because probably the current has gone down. Right, so let us see what the question wants. So the question wants us to calculate the power rating X of resistor Z. So it wants us to know the power that will be dissipated, right? Assuming that Z has a constant resistance, so that does not change. All right, so let us get into the question. So what do we know? We know that the power of Y is now changed to 80 watts. All right, and we know the resistance of Y, that is now 484 ohms. All right, and we're just trying to find the resistance. So that means we need to know the current that is flowing through these resistors, right? So by doing that, we can leverage the power equation where power is equal to I squared multiplied to R. This will be our IRMS value, and we know that our power is 80, and we're trying to find our IRMS squared. We know that that's 484, and our IRMS is going to give us a value of 0.407 amps. All right. Okay, cool. So now we know the current that is flowing through the two resistors, but we need to know the resistance, or let me just say the voltage across Y in order for us to know the voltage across Z, the voltage drops. All right, so we're still going to use our power equation. So now let me just write down a line there. So what is the voltage across Y? Okay. All right. Let us go through it. So this voltage across Y is going to give us, if we substitute it into our power, it's going to be V squared over R as well. That's still going to be 80, and we're trying to find V squared 484, and we're going to find that our V RMS is 196.774 volts. Right, now we said we're doing this to find the voltage drop, right? So that would mean that the voltage through Z could be, keyword could be 220 minus that 196.774, and that is going to give us 23.23 volts. All right, cool. Now, after obtaining such, we're actually doing all of this just to find the resistance there by Z. And how we do it, it means that we essentially need to find the resistance, the actual resistance through Z, and that's why we had to find this V as well as this IRMS, right? But to calculate the power through it, we have to use the rated power, or the rated voltage, or we have to use that, the rated voltage as well as the rated current, but we don't know that, so we're just going to be working with the rated values. All right, so let's just find what the resistance of Z is going to be, because that's not dependent on the rating of the thing, but it's another physical characteristic. Okay, so V divided by I, that's our Ohm's law, 23 divided by our I of 0.40, and we're going to find that we have a resistance of 57.08 ohms. All right, and the average power, this is where we use our rated value, V squared, over our R, and this V squared is going to be 220 squared. See, it's the one that is the rated one, divided by our actual resistance of 57.08, and that is going to give us an average power rating of 847.93 watts. And that is your question.